Hello.
Good evening. Good evening, sir.
Good evening, sir. Good evening to all of you.
Good evening, sir.
Good evening, sir. Am I audible?
Yes, sir.
Okay, fine. So, before I go ahead, I've checked your calendar. It shows that today is the last lecture hour, but it's highly impossible to conclude the course by today. We already lost one class in the holiday. Okay, so up to now, just before today, I had completed 38 lecture hours. For this course, it needs 43 lecture hours. So we are having a shortage of 5 lecture hours. So I hope it is fine with you until I complete.
No problem, sir. Absolutely.
Okay, so I just need your consent for that because according to the calendar, it shows today. But it is highly impossible, I would say.
So not a problem, sir. Maybe other professor has completed. Maybe you can take 2 hours. Also, is it okay for sir? 5 to 6, 5 to.
Okay.
That is also
5. Okay, 5 to 6 is also fine. So your other course is over by today?
Yeah, already over, sir. Already over. Last week it's over.
Okay, fine. So then, what I will do, I will take the class from 5 to 6 from tomorrow.
Right, sir.
Okay.
Right.
Today I will continue with the regular schedule. Maybe from tomorrow I have to reschedule your Google Meet link. I will reschedule it. Okay. So I will make it to 5 o'clock. So probably officially 40 hours are over by tomorrow because we lost one lecture hour in a holiday.
Okay.
But as I said, 40 hours are not enough for this course. I have seen minimum 43 hours are required. So I may take, excluding today, 38 hours are done. So it may take another 5 lecture hours.
Sir, is it possible to take 2 hours per day? That is also okay for us.
So I also don't want to condense too much in a given lecture hour. Okay. I have explored that possibility also, but spending too much time, right? 1 hour is an effective lecture hour. So anything more than that, it may not be effective because you are sitting at the end of the day, right? Evening, already it's evening. Taking 2 hour lecture hours in the evening after your day's work, I do not, prefer that. But if you want, I'm fine with it. I'm flexible. But I would suggest to limit to 1 lecture hour. That is better for you, okay? So that you can grasp the contents, you have time to go through. I have also shared the lecture notes, whatever I have discussed in the class. So I hope you all have received.
Yes, sir. Yes, we have received it.
Okay, so until last class, I have shared the lecture notes. So for the remaining few classes, I will share it. Okay.
Okay, sir.
So I may close it either by Monday or Tuesday.
Thursday, Friday, sir. Is it fine if we can have sessions on Thursday, Friday, so that?
Thursday. Okay.
Because 1 week we'll have for preparation and other.
Okay. So what I will do, I will Thursday and Friday. I need to check my other meetings.
Okay.
I will confirm it on Wednesday if I am taking on Thursday and Friday.
Yes. Thank you.
Okay, sir. Thank you, sir.
Okay, is my screen visible to you?
Yes, sir.
Please answer your attendance. Aditya Kumar.
Present.
Anand.
Present, sir.
Ananda Kumar.
Present, sir.
Arnachalam.
Present, sir.
Hasan.
Present, sir.
Hemant.
Present, sir.
Jagan.
Yes, sir.
Kesav Prasad.
Yes, sir.
Lakshmi Narayanan.
Present, sir.
Prabhakaran.
Present, sir.
Prem Vinayak.
Present, sir.
Rahul.
Yes, sir.
Roshan Kumar.
Yes, sir.
Sabish Kumar. Satish Kumar.
Present, sir.
Titus.
Present, sir.
Vallish.
Yes, sir.
Vigneshwaran,
Present, sir.
Jairaj,
Yes, sir.
Vikash,
Present, sir.
Vivekanand, Yadav,
Yes, sir.
Yuvraj.
Present, sir.
Okay, I just wanted to confirm Vivekanand is absent, right?
Yes, sir. He is not available.
Okay, fine. Okay, so welcome back. We are in the last part of the chapter 5. In the last part, we are now discussing the factors that influence pollutant formation in spark ignited and compression ignited engine. We have already discussed the factors. So when I say factors here, it refers to engine design and operating variables or parameters that are influencing pollutant formation. Again, pollutants here refer to primary pollutants emitted from IC engine. They are also called regulated pollutant. We need to reduce the concentration of these pollutants emitted into ambience because they create health effects. So we have so far discussed the factors that affect pollutant formation in spark ignited engine. In the last class, I started my discussion on the factors that affect pollutant formation in CI engine, compression ignited engine. I will continue that now. So these are the variables, engine design and operating variable that affect pollutant formation. So design variables you need to carefully optimize when you design the engine. And as we know, in compression ignited engine, we have to control 4 regulated pollutant: NOx, particulate matter, HC and CO. In NOx, we have both NO and NO2, unlike SI engine, where NO2 concentration is negligible. Here, it can go up to 30%. So we need to control these species emitted from the engine. That's why we need to look at the variables that have an influence on this pollutant so as to carefully optimize this variable such a way that the pollutant levels are less in the engine. That is our objective. So if you look at compression ratio, so when we analyze the effect of these variables on pollutant formation, you have to recollect the mechanism involved in forming this pollutant, which we have already discussed. Okay, so we need to relate how this particular variable affect the mechanism involved for a particular pollutant. That is how we analyze the effect of these variables on the pollutant emission. So when you talk about compression ratio, it's an important design variable. As we know, it affects performance as well as pollutant emission. Now here we are looking at how it affects pollutant emission in a typical diesel engine. Compression ratio, as we know, for a CI engine, it varies anywhere between 14 to 22. That's a normal compression ratio range for a CI engine. We need to carefully fix a particular number based on a given CI engine. CI engine is most versatile, as we have seen. You have a large application segment for CI engine. Based on the type of application, based on the type of CI engine that we handle, we need to carefully optimize this. Now let us look at how this affects pollutant. Let us consider that we are increasing compression ratio. If we increase compression ratio, what effect it will create on the combustion? Hello? If we increase compression ratio, what effect it will create on the combustion process?
It will reduce the premix phase, sir.
It will reduce the premix phase. Okay. Anything else? What is the gross effect? Suppose if you are increasing compression ratio, basically you are compressing the charge to a higher pressure and temperature level, right?
Right, sir.
If you do that, what will be the gross effect of this on the combustion phenomena? So obviously temperature will increase. Do you agree?
Yes, sir.
Yes, sir.
So overall, a gross effect, I would say, that's why I use the word gross effect. Overall effect of rising compression ratio of a CI engine is, it is going to increase temperature as compared to running engine at a lower compression ratio. When you run engine at higher compression ratio, the temperature is going to increase. When temperature increases, we know it is going to increase the NO levels. So NOx will increase with the higher temperature. Okay, especially thermal NO. So I would even put it this way. So you are going to increase the thermal NO level because temperatures are high, and NOx is primarily dependent on the temperature values. This is the effect of increasing compression ratio. You can expect higher NOx level in the engine because thermal NO is going to be high. What will happen to the other pollutant? For example, particulate. Particulate, the major component is soot. So what will happen to soot with a higher temperature?
It will increase.
There are two phenomena with respect to soot. One is formation, the other one is oxidation. Formation mechanism we discussed already. Pyrolysis is a starting point, right? So pyrolysis is going to create soot precursors or soot nuclei. From there you get into other process wherein it will start to increase the soot concentration levels in the engine cylinder. So formation is dependent on temperature, okay? But there is another thing, oxidation. And I said that almost 90% of total soot formed is oxidized in the cylinder. For oxidizing soot, what you need primarily is temperature. You will have sufficient oxygen level in a diesel engine because you always run with excess air. So you have oxygen. Once you have the required temperature, oxidation rate is going to be high. So out of the two phenomena, formation and oxidation, both are going to be high with a higher temperature. But among these two, it is known that soot oxidation is more dominant. You are going to have a very high soot oxidation level when the temperature increases. So overall effect of higher temperature or higher compression ratio on the soot is it is going to come down. Again, you could see a trade-off here. NOx increases, soot drops. Soot drops here primarily because oxidation of soot is high. And HC level, as Roshan you pointed out, the premix phase combustion is less. HC level will come down primarily because of the delay, ignition delay effect. You recollect the mechanism of HC in CI engine. One of the important mechanism is over-mixing. Over-mixing happens when the delay time is longer. Now here, when you increase compression ratio, the ignition delay time is going to be shorter because of the temperature effect. You are compressing air to a higher pressure and temperature at the time of fuel injection. Ignition delay will come down, over mixing will come down, so HC levels will come down. Okay, similarly CO can come down because of the temperature effect. CO and HC are also sensitive to temperature because it affects the oxidation rate of HC and CO. So you can see here that except NO, the other primary pollutant may come down if you run engine at a higher compression ratio. About the combustion chamber design, so we already discussed about combustion chamber design in the third chapter for CI engine. So one of the primary consideration when you design combustion chamber, we have discussed, you need to increase the rate of mixing. So to increase rate of mixing, what will be the focus here is we have to increase wall, we have to increase squeeze. This is one of the primary consideration when we design combustion chamber for CI engine. We are going to increase wall and squeeze. When you increase wall and squeeze, rate of mixing, fuel air mixing is going to be improved. So you have an improved fuel air mixing. So what will be its effect on the combustion? Can I say the bond rate increase?
Yes, sir.
So you're going to have a higher bond rate. This is one of the important effect of combustion chamber. When bond rate is increased, obviously the temperature levels are high because you are burning with a higher rate, meaning heat release rate will be high, energy release rate is high, temperatures are high. The other important aspect when we design combustion chamber is surface to volume ratio. So you can generally, the objective would be to reduce the surface to volume ratio because this is affecting heat loss. To increase thermal efficiency, you will bring this down. When surface to volume ratio is less, heat loss will be less because heat loss depends on the area available for the transfer of heat across the wall. Okay, when we talk about heat loss, here we are talking about wall heat transfer losses. That is the heat loss from the engine cylinder to the coolant. Okay, it's also called wall heat transfer loss. It's a function of surface to volume ratio. So when you reduce surface to volume ratio, heat loss is less. When I say heat loss is less, what will happen to in-cylinder temperature? High. So you can see here that overall objective of combustion chamber design in a CI engine is to increase the bond rate, increase mixing. That is going to raise the temperature. You are also going to retain less surface to volume ratio from the perspective of increasing thermal efficiency and reducing heat loss. That will also increase temperature, right? That will also increase temperature. So this rise in temperature in the cylinder will reflect in the primary pollutant level. NOx, NO will increase. Thermal NO will be high. What about the other pollutant? What will happen to soot?
It will decrease, sir, because oxidation will also increase.
Will decrease for two reasons. One, improved oxidation with higher temperature. Any other effect because of better mixing in terms of soot formation? Can I say Phe-rich regions reduces due to better mixing? So you are increasing swirl and squeeze. This will result in better air fuel mixing. Can I say that this will reduce local rich region?
Yes, sir.
So the overall effect will be Phe-rich regions are less, temperature is high. Okay, so this will reflect in lower soot emission. Again, you see a trade-off here. NO is increased, soot is decreased. With the decrease in Phe-rich region, CO will also come down since the temperatures are high. SC will also come down due to improved oxidation. CO and SC will come down due to improved oxidation. CO comes down also due to less Phe-rich region because CO forms due to insufficient oxygen, right? So with the Phe-rich region, reduction in Phe-rich region, you can expect CO to be lower. So combustion chamber design, by carefully doing the combustion chamber design, you can bring down all the three primary pollutants, CO, SC and soot. Only problem will be there will be higher NOx. So you need to adopt appropriate NOx control methods. The next one is about dead pockets in the combustion chamber. So you have already discussed, we have already discussed about Krubais flow. Krubais is one of the dead volume. The effect of dead volumes or dead pockets is different for SI and CA engine. How it is different? Because in SI engine, you are handling pre-mixed fuel and air. You introduce fuel during intake stroke. Fuel air mixture is entered into the cylinder and which is what is compressed. So you have a well mixed fuel and air that is being compressed in a SI engine. Whereas in a CA engine, you are compressing only air. Fuel is introduced during later part of the compressor stroke. Near the end of compressor stroke, you are injecting fuel. Until then, you have only air remaining in the cylinder. So what this dead pockets in the combustion chamber? Dead pockets, one of the major dead pocket is crevices, similar to what we have discussed earlier. So crevices, valve seats, intake, exhaust valve seat, all these are dead pockets. So what these dead volumes or dead pockets will do in a CA engine is, it is going to trap air. It is going to trap a considerable volume of air out of the total air quantity in the cylinder. A considerable fraction of air will go and get locked in this dead volumes. For example, crevices. So now you can think of what effect this will have on the pollutants. You will have a reduced air level in the cylinder because of the dead pocket. So what effect it will create on the primary pollutants?
The soot will increase, sir, because
yes.
oxygen.
Exactly. So when I say air levels are reduced, okay, so air levels are reduced in the combustion chamber. So this will reflect in more Phe-rich regions. So you have a reduced air mass in the cylinder. Reduced air mass in the cylinder will reflect in high Phe-rich regions locally. This will directly affect the soot formation. Soot formation is going to be high when you have a higher dead volumes in the combustion chamber. You are actually reducing air availability. By doing that, you are increasing the local rich region. Soot will increase, CO will increase. This is an important effect of having more dead volumes or dead pockets in the combustion chamber. And obviously, combustion quality will deteriorate, meaning temperature will come down because you have a less burn rate. This will have a low NO. Again, you see a trade-off here. With more dead pockets, deteriorated combustion, you will have lower NO. Please note here that NO levels are always high when the combustion is better. Okay, NO levels are always high when the combustion is better because better combustion leads to higher temperature. Deteriorated combustion will leads to lower temperature, so that will have a lower NO. Okay, so this is the effect of dead pocket in the combustion chamber. They are trapping air, thereby they are increasing Phe-rich region, increasing soot or CO, but NO will come down. NO comes down due to temperature effect. Deteriorated combustion reduces temperature, reduces NO. The other design parameter which is relevant only for CI engine application is injector location. So when I talk about injector location, so you can locate injector. I will show you 4 possible ways wherein you can locate the injector. So this is one option. This is another option. Option 3. This is option 4. So you can mount injector with any of these options. So option 1, you are mounting injector along the axis. So it is a centrally mounted injector. Second one, you have an offset. So you have an offset injector, that is case 2. Injector is away from the axis. Case 3, it is centrally mounted. Injector is centrally mounted, but you have an angle. Okay, the first one is aligned to the vertical axis. The second one is that injector is at some angle with respect to vertical axis. Okay, so it's an inclined injector. The last one, it is offset as well as it is inclined. Now, among these 4 options, which one will you prefer and why? I'm posing this question to you. Which one you will prefer and why?
The 1 number, sir. 1 number is preferable.
For the spray cone angle to be sufficient and
so all of you agree that 1 is preferable? Whether all of you agree that injector mounting 1 is preferable?
Yes, sir.
Yes, sir.
Why? Is my follow-up question. 1 is preferable. Why this is preferable?
Because for the option number 2, the liquid fuel can hit the wall. Because
liquid fuel can hit the wall. Okay. One of the spray may go and hit the wall. Okay.
Right, sir.
Please always remember that you have n number of spray, not one single spray. Generally, you will go with multiple sprays. Okay. So 1 will hit. And option 3?
Option 3, same, sir. Again, it can hit the wall. Spray.
Can I say that it may even hit the cylinder head?
Yes, sir. It can hit the cylinder head also.
Okay. Option 4?
Option 4 will be better than 3, but still it is again this case of this thing only, sir. Like it
so wherever it is nearer to the wall, you can expect that spray to go and hit the wall.
Right, sir.
Any other problem with the offset and inclined injector? Any other problem?
Yeah,
Exactly.
spray penetration length will not be uniform and
spray penetration length will not be uniform. Perfect answer is uneven distribution of spray to the given air. So what you have to ensure when you mount the injector is you ensure that equal quantity of air is available for all the sprays. So you have multiple sprays based on the number of orifices available in the injector. You will have multiple sprays emerging from the injector. Now what we have to ensure is for each spray the air volume available is uniform. This is called uniform fuel distribution or air distribution inside the cylinder. This is one of the important consideration when you mount the injector because uneven fuel distribution. When you suppose if you have an offset injector, the spray emerging from this orifice will have more air. Whereas the spray emerging from the other end will have less air to be utilized. So air utilization is non-uniform if you have an offset injector. The other problem, as you rightly pointed out, the spray may go and hit the wall impingement effect will be there. Similarly, with the inclined injector, the spray may even go and hit the cylinder head. Okay, so you will have spray hitting the solid boundary. That is one potential problem. Second important problem is uneven air availability for all the spray. One spray will get more air, another spray will get less air. So you have a kind of non-uniform fuel distribution inside the cylinder. In other words, the quantity of air available for each spray is going to be different. When quantity of air available for each spray is different, you can imagine what will happen to mixing process, fuel air mixing process. So fuel air mixing process is going to be highly non-uniform. We already discussed that in diesel engine, the major problem is heterogeneous mixture. And because of heterogeneity, the phi global and phi local will deviate more. If this deviation is high, right? So homogeneous mixture is ideal SI case. These two are same. Heterogeneous mixture is the actual case in CI engine. Because of that, you have a difference in local and global. And if this difference is high, you will have a problem of very high pollutant level. So if you don't do this centrally mounted injector along the axis, if you go with option 2, 3 or 4, you're going to have a problem with phi local, in the sense that you're going to have a very high rich region in some of the locations inside the cylinder. This is going to increase soot. The immediate effect of offset injector or inclined injector is very high soot level, because non-uniform mixture distribution inside the cylinder, heterogeneity in the cylinder. When I say heterogeneity, it is PLR mixture heterogeneity that will reflect in the phi value, local phi value. It's going to be highly variable, in the sense that you may have regions with very little air available that will shoot up the phi value, that will shoot up the formation of soot. You will have a very high soot level. That's a potential problem with the inclined or offset injector. So you need to avoid. Generally, this is preferred. This should be avoided from the perspective of reducing particulate emission, which is a major pollutant from diesel engine. Okay, so you have to go with option 1 to reduce soot. But the problem is, if you have a better combustion, NO will high. So with this option, you can expect high NO, low soot, low CO, low HC. Only problem is you will have NO levels high. That is unavoidable. Again, there is a trade-off. There is a better combustion that reduces all the 3 primary pollutant. For the same reason, better combustion increases NO levels. Clear? Okay, so next we are checking with the operating variable. You have 4 important operating variable in a diesel engine. Among this, I would say that the option 1 is the most important variable. Load and speed, it is out of your control. You need to run engine based on different load and speed. Okay, but whereas the first one, you need to carefully optimize. This operating variables needs to be optimized dynamically when you are running the engine. So that's why you need to have a control system, closed loop control system in place. This closed loop control system will get signals from the sensor, and it has to dynamically optimize this injection parameter such a way that the primary pollutant levels are less in the engine. 2 important injection parameters are, one is timing, fuel injection timing, and second one is pressure. These 2 are controllable if you have an electronic injection system, and these 2 cannot be controlled if you have a mechanical system. Mechanical system don't have any flexibility in varying the injection parameter. That's why we need CRDI, Common Rail Direct Injection System. Almost all the on-road vehicles are with CRDI system. We don't use mechanical system. Except in off-road stationary diesel engine, we generally go with flexible electronic injection system in diesel engine. So it means you can vary this timing and pressure. Now let us look at the effect of this injection timing and pressure on the pollutant level. So when I talk about timing, you have 2 options. One is with respect to TDC, where you are spraying the fuel. So you can either spray it far away from TDC. This is what we refer as advanced injection timing, or closer to TDC, which is what is retarded injection timing. So when you are spraying the fuel spray, so let us say this is 1 and this is 2, in cylinder conditions are totally different at these 2 points. Okay, this is, let us say, P1, T1, and 2, let us say it is P2, T2. That is the in cylinder pressure and temperature condition. Now we are looking at how this is affecting the primary pollutants from diesel engine. Let us say you are going with retarded injection. When you go with retarded injection, what will happen to pressure and temperature?
It will be higher than point number 1.
Pressure and temperature is high. When pressure and temperature are high, what will happen to the first phase, delay, ignition delay phase?
It will be less.
It will be less. When this is less, what will happen to subsequent premix combustion? Let us say PP is premix combustion.
It will also be small.
It will be less. then what will happen to diffusion combustion?
It will be dominant.
It will be high. Let us say DP, diffusion phase combustion, it's going to be high. So this is what is happening when I retard the injection. Now we are looking at how this is going to affect the pollutant levels. When ignition delay is less, please note that premix phase is the period where the combustion is instantaneous. Okay, so when premix phase is less, the temperature levels are going to be less. Okay, and diffusion phase is primarily limited mixing. When I say a more dominant diffusion phase combustion, what will happen is Phe-rich regions are going to be high, because diffusion phase is the time where you give very little time for fuel air mixing. During the diffusion phase combustion, the time available for fuel air mixing is very limited. So what you can expect with a dominant diffusion phase combustion, Phe-rich regions are going to be high. What you can expect with a less dominant premix combustion, in-cylinder temperatures are going to be less. Now you can easily analyze what will be its effect on the pollutant. So what will happen?
NOx will come down, soot will increase.
NO will come down, soot will rise. Similarly, CO will rise. CO is also function of oxygen availability. When I say Phe-rich regions are high, CO will be high. So with retarded injection, you know that retarded injection is one of the well-known NO control method. When NO levels shoot up, ECU will sense that and it will immediately delay the injection timing such a way that NO levels are put under check. Okay. That's why I say that you need to have a closed loop control system in the engine. You have to closely monitor the pollutant level. When NO shoot up, one of the most effective method to reduce NO level in the engine tailpipe is retard the injection timing, because that is going to bring down temperature, that is going to bring down NO. But the other effects are you will have a rise in soot, rise in CO, because diffusion phase is increasing, Phe-rich regions are increasing. SC level also may come down initially, because with retarded injection you have a less delay time, so over mixing is reduced. But with significantly retarded injection timing, you may have a SC level increase, primarily because of less time available for oxidation. Okay, less time available for oxidation, and temperature is also decreasing when you keep on reducing or retarding the timing of injection. Okay, so you need to carefully optimize injection timing based on the level of pollutants in the engine tailpipe. Okay, that's why you need to monitor the pollutant levels in the tailpipe. Accordingly, you need to fix this timing, fuel injection timing. So overall, we could see a significant effect of timing on all the four pollutants, primary pollutant. Now let us look at the pressure. Injection pressure is again a variable. You can inject fuel anywhere between 300 to 3000 bar. That's a normal range of injection pressure that you can vary. So now let us look at, suppose if you are increasing the injection pressure. Now let us look at how it affects the primary pollutant. What will happen when you increase the injection pressure?
Mixing will be more uniform. Automation will be better.
Atomization is the immediate effect. So you have better atomization when I increase injection pressure. When atomization is better, then vaporization is better, mixing, fuel or mixing will be better. Okay. So when fuel or mixing is better, what will happen to Phe? There will be more homogeneous mixture in the cylinder. What I mean to say here is Phe local will try to approach Phe global as close as possible. Heterogeneity will reduce in the cylinder. When heterogeneity is reduced in the cylinder, definitely Phe-rich region will reduce. This is one of the important effect of increasing injection pressure. Phe-rich region will come down. Any other important effect because of better mixing?
The soot will come down, sir, and SC will come down.
Yes. Now, in terms of combustion, any other effect? Burn rate will increase. Can I say? So when burn rate increases, temperature will rise. Okay. So two important effects of increasing injection pressure. One, mixture heterogeneity is reduced, Phe-rich regions are reduced. Second effect, temperature will be high because of high burn rate. The cumulative effect of these two will reflect in very low soot level, very low CO, high NO. I have not listed out HC here because if the injection pressure is too high, you may have spray wall impingement. We discussed that is one of the mechanisms that cause HC. So if pressure is too high, you may have wall impingement. If wall impingement is there, you can expect high HC. But if you carefully fix the pressure based on the bore, cylinder bore, you can avoid spray impingement. If you avoid spray impingement, HC also will come down. So the overall effect on HC is based on given engine and the given engine in the size of the given engine in the sense size of the engine. Second parameter is the magnitude of the pressure. Right? It should not be too high if you have a small engine. That will cause spray wall impingement. If you avoid spray wall impingement, better burning will reflect in less HC because, as I said, temperatures are going to be high. It will improve HC oxidation. Clear? So next, let us look at what is the effect of load on the. So we know we are going to run diesel engine at different load. Now let us see what is the effect of load on the primary pollutant. When load is increased, how do you increase load in a diesel engine?
By controlling the amount of fuel.
So when I say I'm increasing engine load, I'm increasing injected fuel mass. So when fuel mass is increased, what will happen to temperature? You're burning more. So obviously temperature will be high. What will happen to Phi? Phi is high. When I say Phi is high, can I say air fuel ratio is reducing? Yes or no?
Yes, sir. Yes, sir.
So you have higher temperature at higher load. Two important effects at higher load. Higher temperature, Phi is high. Compared to low load, in a relative sense, you will have a higher temperature, you will have a higher Phi. When Phi is high, you can expect Phi rich regions also to be high because air fuel ratio is decreasing. So now you can comment on what will happen because of this to the primary pollutant. What will happen to primary pollutant?
NOx will come down and soot will increase.
No, NOx won't come down because temperature is high, right?
Oh, sorry, yes.
So NOx will be high, soot will also be high. Only at high load you can see that there is no trade-off. Both NO and soot are increasing. NO is increasing due to temperature effect. Soot is increasing because of increased fuel mass. Please note that air mass is always constant. Keeping air mass as constant, when you increase fuel mass, air fuel ratio is going to come down. When air fuel ratio come down, Phi local rich region are going to be high. So you can expect more soot formation at high load compared to low load. Low load, you have more air. Okay, so soot will be high, NO will be high, CO is also high because of rich region. Okay, so all these are high. HC may come down due to temperature effect. Okay, because you are burning more the temperature, better the oxidation. CO will be initially due to temperature effect, CO may come down, but when suppose if Phi reaches a threshold value of say 0.7 or so, CO will also start to rise. Initially due to better temperature, CO and HC will come down, but CO will increase if Phi is more than 0.7. Based on the injected fuel mass, the magnitude of Phi is going to be different in different engine. Okay, that's why I've given a typical threshold value. Until that point of time, with increase in load, CO will come down, but above 0.7, CO will also increase with increasing load. Next, we have the speed. When I say that I'm increasing speed, basically the turbulence level in the engine will be more. Swirl and squeeze air motion inside the cylinder is going to be higher. So higher the engine speed, turbulence increases. It's a function of engine speed. So air motion in terms of swirl, squeeze is going to be high. This will reflect in higher bond rate because this will reflect in better mixing. Higher bond rate. So obviously the temperature will increase at higher speed. Higher temperature will reflect in NO, high levels of NO. Higher temperature will also improve oxidation rate of soot, CO, and HC. So they may come down, soot, CO, and HC. But you should also note that with increase in speed, the time available for all this will also come down. Engine is running at higher RPM, engine cycle time will be less. So the time available for oxidation of SC, CO as well as soot will come down. Okay, so there are two contradicting effects here with speed. The time is less, the temperatures are high. Due to high temperature, the oxidation rate is high. So the overall final value of SC, CO or soot is dependent on the magnitude of the speed. Okay, but NO you can say that it's going to be high with increase in speed because of better burning and higher temperature. Next, we have exhaust gas recirculation. This can also be optimized. I will talk more about exhaust gas recirculation in the next chapter when we talk about pollution control. So what we are doing here is we are recirculating a fraction of exhaust gas back into the intake manifold. So this is exhaust. So you are recirculating exhaust gas. This is intake manifold. This is exhaust manifold. So when I say that I'm recirculating exhaust gas, I'm tapping a fraction of the exhaust gas from the exhaust line and sending it back to the intake line. In the intake line in a diesel engine, you know you are inducting only air. Okay, and fuel is sprayed here inside the cylinder. So exhaust gas is mixed with air and it is sent into the engine cylinder. Now, if this is the case, what will be its effect on the combustion phenomena? Two important effects. One, temperature will come down. Second one, oxygen will come down. Oxygen will come down due to displacement effect because exhaust gas is displacing a considerable fraction of air in the intake system. That's why you have less air going into the engine. This is what is the displacement effect or dilution effect. Oxygen levels will come down. Temperature will come down because of the constituents of EG, exhaust gas. You primarily have CO2, H2O, complete combustion products in the engine. These are triatomic gases. They have a high specific heat. When the specific heat is high, the temperature will come down. This is called heat sink effect. It won't allow the combustion system temperature to rise. Higher specific heat component will absorb the heat and it won't allow the combustion temperature to rise. That's the reason why you have a drop in temperature. So this is the effect overall or important effect of recirculating exhaust gas into intake manifold. Now you can comment on what will happen to the primary pollutants.
NOx will come down, soot will increase.
One of the important effect of EGR is NO control, NOx control. NO will come down significantly when you recirculate exhaust gas, primarily because of these two effects. You have less temperature, you have less oxygen. So NO kinetics will slow down. The rate of formation of NO, which we discussed through Zeldovich mechanism, says that with less temperature, less oxygen, you will have less NO. So this is actually one of the reasons why we use exhaust gas recirculation. It's one of the NOx control method. Okay, so we will bring down NO level by recirculating exhaust gas. But there are other effects. Soot will be high. There will be trade-off because soot will be high for the same reason. Less temperature, less oxygen. Oxidation rate of soot will be less. So when I say less oxygen, Phe-rich region also increase inside the cylinder. So soot will be high with exhaust gas recirculation. For the same reason, CO is also high because you have insufficient oxygen in the cylinder. Okay. Similarly, HC will be high primarily due to temperature effect. You have lower temperature, so less oxidation. Less oxidation leads to high HC levels. Okay, so this is the effect of exhaust gas recirculation. By recirculating exhaust gas, you are effectively controlling NO level, but the other three primary pollutant will increase.
So this is similar to wall overlap in what I mean to say SI engine, right?
Yes, yes. I will talk about wall overlap in the next chapter. Similar effect is there. By retaining residual gas, whatever effect you have, same effect will be there when you recirculate exhaust gas. In fact, residual gas or exhaust gas, they are same product, combustion product. Okay, you have different terminologies based on how it is retained in the cylinder.
Thank you, sir.
Okay. So with this, I conclude chapter 6. Now I am moving to chapter 5 is concluded with that. Now we are moving to the next chapter in the second module, chapter 6, which is about pollutant control method. So these are the contents that we are going to discuss in this chapter. So far in the previous chapter, we discussed the mechanism involved in forming primary pollutant and what are the factors that influence pollutant formation, primary pollutant formation in SI and CA engine. Now with that understanding, we are going to look at the available control methods. This is very important to learn because you need to control the pollutant level below the legal mandate. There is an emission mandate which is a legal requirement. Okay, otherwise you cannot sell the vehicle on the market. Any new vehicle cannot be launched until otherwise the legal emission requirements are met. So we have to control the pollutant level below the legal limits. So we should be familiar with the control methods that are available. And before we discuss control methods, very important to learn the mechanism upon which the pollutants are formed and also learn the factors that affect or influence the pollutant formation. So with the understanding of those mechanism and factors, we are moving and looking at the methods, control methods. So the control methods are broadly classified into two types. One is called in-cylinder method. Second one is after treatment method. In-cylinder method target to reduce pollutant level in the cylinder itself. As the name implies, we are going to reduce the pollutant level inside the cylinder itself. Whereas in the after treatment control, we don't bother about how much a pollutant is formed in the cylinder. Rather, we will control the pollutant level in the tailpipe, engine exhaust pipe or tailpipe. Okay, so pollutant concentration is reduced in the tailpipe before the pollutants are let out into atmosphere. That's why it is called after treatment. You are not controlling the formation of pollutant, rather you allow it to form, and after the pollutants are formed, you are controlling it. That's why it is called after treatment control method. So I will give more detail about what are the available in-cylinder control options and what are the after treatment control options you have to reduce the pollutant levels from SI engine and CI engine. So this is what we are going to look at in this chapter 6. So before we go and discuss about in-cylinder and after treatment control method, let us have a quick look at the exhaust gas condition. It's very important to know the exhaust gas condition in SI engine and CA engine before we talk about in-cylinder and after treatment control. Especially for after treatment control, it's very important to learn the difference between the exhaust condition in SI engine and CA engine. That's why I have given some overview of exhaust gas condition in a SI engine and CA engine before I discuss the control methods. In a spark ignited engine, we know very well, we have discussed this many times. Operating free range is 0.9 to 1.2. So you are close to stoichiometry or slightly rich. Because of this operating fee range, you will have products of rich mixture combustion because you are going up to 1.2. You will have more rich mixture combustion products, for example, CO and HC. We in chapter 2 discuss both the thermodynamic aspects of combustion. There we discuss what will be the products of combustion with a different fee value. You have to just recollect that. We know under rich mixture combustion condition, you will have very high CO level, very high HC level. HC is a representative hydrocarbon. Okay, you will have more unburned emission and CO emission because you have insufficient oxygen with rich mixture. And the temperatures are going to be very high compared to CA engine. You could see that they reach 300 to 1000. When it will be 300, when it will be 1000? I'm talking about exhaust gas temperature.
No load and full load?
Yeah, exactly. So this is at low load. This is at full load. So based on the load, the quantity of mixture that you burn in SI engine is going to be different. We know we are controlling that using a throttle valve. So by regulating the quantity of the mixture using a throttle valve, You are actually controlling the quantity of mixture burnt in the engine that will reflect in the combustion temperature, that will also reflect in the exhaust gas temperature. It varies anywhere between 300 to 1000. This is a normal or nominal exhaust gas temperature range for any given spark ignited engine. And the products are rich mixture combustion. This is the typical condition of SI engine exhaust gas.
It is insulated.
Sir, the temperature 1000 degree, it's inside the cylinder or?
No, I am talking about exhaust gas temperature.
Sir, tailpipe or in between the process areas?
Tailpipe.
Okay.
Tailpipe. If you do the experiments with SI engine, you can easily measure this temperature using a thermocouple. If you fix a thermocouple in the exhaust line in the tailpipe, okay, you will get these numbers.
Okay, sir.
So we are basically looking at the exhaust gas condition primarily from the perspective of after treatment control. Okay. So typical SI engine exhaust gas will be at this temperature range, and it will have more products of rich mixture combustion like CO and SC. These are the typical SI engine exhaust gas condition because of the operating fee range, which is from 0.9 to 1.2. Now, when you look at CA engine exhaust gas, conditions of CA engine exhaust gas, before that, you know very well that the CA engine run with a fee value of 0.4 to 0.8, always less than 1. It's a lean combustion, and we have discussed that we use up to 30 to 50% XSR. XSR means more than stoichiometric proportion. So fee is less than 1, you use high XSR. Because of that, the temperatures are less, operating temperatures are less. Exhaust temperatures are also less. It varies from 100 to 500. Again, this is at no load. This is at full load. So you have, this is a nominal or normal range of exhaust gas temperature, and a typical CA engine, it's going to be less, considerably less compared to SI engine. The difference comes due to operating fee range. Operating temperatures are high in SI engine, they are less in CA engine because of XSR, and you will have products with the more lean mixture combustion. You will have excess oxygen appearing in the engine exhaust. So CA engine exhaust will contain more lean product. SI engine exhaust will contain more rich combustion product, and temperatures are considerably different. Now, when you look at what you need to reduce SC in the tailpipe, you have to oxidize SC. To oxidize SC, typical temperature requirement is above 600 degrees Celsius, 600 degrees Celsius. CO to oxidize is further high. Typical temperature required is around 700 degrees Celsius. So you could see that the 600 and 700 are never reached in a typical normal CA engine operation, where the gas temperature is around 500. That's a max value. SI engine, it is possible under certain operating condition. When you move towards full load, it's possible to reach higher temperature, meaning you can oxidize SC and CO in the tailpipe also. But this is not possible in a CA engine. Okay, but in presence of catalyst, if you have a catalyst based control system, the temperature you need is less than 250 degrees Celsius. This is one of the most effective method of controlling SCCO. You need to use appropriate catalyst, because you could see that it considerably reduces the temperature requirement for oxidizing unburned hydrocarbon and CO. So HC is oxidized to H2O and CO2. CO will be oxidized to CO2 in presence of a catalyst. Even at a lower temperature, up to 250 degrees Celsius, you can effectively bring down HC and CO. So this is one of the most effective method for controlling HC and CO. Otherwise, you need a high temperature, which is not possible to achieve in CA engine. In SI engine, it is possible under certain operating conditions. For NO and NO2, you have to reduce it. So HC and CO has to be oxidized. NO and NO2 has to be reduced to nitrogen before it is let out into atmosphere. So it's a reduction process. HC and CO or oxidation process. For reducing, you have to follow catalytic route only. You cannot follow thermal route, meaning there is no point of talking about oxidation of NO or NO2 here. It's about reduction of NO and NO2 to nitrogen. So for reducing it, you need a suitable catalyst again. So you have to follow a catalytic route, use appropriate catalyst, reduce NO and NO2 to nitrogen before the gas is let out into atmosphere. For particulate matter, since it's a solid particle mostly, and solid particle carry liquid particle, as we discussed already, the composition of PM, you have to filter it. What you need is a filter to nano size or based on the PM size, you have to use appropriate filter to remove the particle and let out clean exhaust gas into cylinder. So don't let out the soot laden exhaust gas into atmosphere. You filter it out using a diesel particulate filter and let the clean exhaust gas go out of the engine. So what you need is a particulate filter for removing PM. For NO and NO2, what you need is a suitable catalyst to reduce. For HC and CO, what you need is a suitable catalyst to oxidize. So these are the exhaust condition, and this is how you need to reduce the concentration of these primary pollutant. It's time up. I stop here. If you have any questions, I can take your questions.
So this, for particulate matters, so the filter, when it filters down, the residues will remain within the engine's tailpipe itself, sir?
Yeah, it's going to remain. There is something called regeneration. I will give more detail. What I have given now is just an overview. Okay.
Okay.
So once the particulate filter is loaded with the particles, you have to periodically remove it. That process is called regeneration.
Okay, sir. Understood.
Otherwise, it is going to create back pressure in the exhaust.
Back pressure. Yes, sir. Yes, sir.
So it is going to increase the fuel consumption. So you have to clean the DPF once the load reaches a threshold value.
Okay, sir. Sir, in any case, when we are having a filter on the tailpipe for the particulate matter, still it will create a bit of a back pressure for the exhaust.
It's going to create back pressure, definitely. It's one of the shortcomings of this. It's going to create back pressure, but it is not so high with a clean filter. So they will carefully design, because this is one of the important consideration, pressure drop in the exhaust line. When they design the DPF, they will carefully design it in such a way that pressure drop is not so high. Otherwise, you will have the problem of higher fuel consumption in the engine.
Okay, sir. And how about the regular cleaning of these filters? That will be just like periodical maintenance of replacement?
Yeah, periodical maintenance, periodical regeneration. You need to have a closed loop sensor control system. You have to monitor the pressure drop carefully. Once it reaches a threshold value, regeneration process will start. Filter will be cleaned.
Understood, sir. It will run automatically based on...
Yeah, it is an automated process.
Understood, sir. Clear, sir. Thank you, sir.
Okay. Fine. Any other questions? Okay, I'll stop here. I'll see you tomorrow at 5 o'clock. Okay, is that fine?
Yes, sir. No issue.
Yes, sir. Fine. Thank you, sir.
Bye.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.